Greetings, junior scientists and citizens, great big weird wonderful world in which we live. As always, I'm your humble science communicator, the Great Orbex, joining you here from Physics Hollywood, California, in SSC 1101A at the University of Guelph. That's right, we are back on the Guelph Physics live stream, streaming out to the internet. I welcome everybody in. It's exciting. We've returned with our incredible background. And for the first time in the history of the Guelph Physics live stream, producer Saxum is in the room with me. It's not entirely remote. It's exciting. It's thrilling. And we're here tonight to have an exciting journey to the planet of robots. Now, the excitement abounds this evening. Oh, I'm sorry, I'm reading things. We're getting communications thrown back and forth. I've forgotten how exciting things are in the world of live streaming and live chatting. But thanks for tuning in, everybody. We're joined tonight for our third annual live stream with the Royal Astronomical Society of Canada, Montreal chapter. And if you're joining us from their feed, I'd like to welcome you into the Guelph Physics feed as well. If you're joining us from the Guelph Physics feed, go over and check out the Royal Astronomical Society of Canada, Montreal chapter feed. They do some good work over there. Feel free, as always, it's a live stream and we have our live comment section coming in through. If you have questions for our speaker about the planet of robots, then you can post them right there, or just questions about physics in general or physics at the University of Guelph. We'll be happy to answer them as they come up. Wow, what an exciting night. I don't want to keep you too long from our speaker because he has an incredibly long presentation prepared for us this evening, which I'm hoping will be trimmed down a little bit. But without any further ado, I'd like to bring in our co-streamer for the evening, and I'd like to introduce Kareem Jaffer. Saxon, bring him up on the big screen.
Hey, Orbex.
How's it going tonight, Kareem? I see you're joining us from the planet of robots itself. How can you even breathe there?
Well, very carefully.
If my knowledge of the surface of Mars, which comes entirely from watching the movie Total Recall over and over again, is true, I would expect to see your eyes bugging out, but I feel like perhaps this is just one of those magic tricks that the internet plays.
But let's not forget that when it's Martian summer, in some places, it is warmer than Winnipeg or the Yukon or even Montreal some nights.
Sorry, you're cutting out there. Was that supposed to be a joke, or was that a...
I knew the compliment was too good to be true.
Well, I'm just being fun. Well, thank you for joining us, and thank you for bringing in all of the RASC people onto this stream. It's always exciting to interact with them. You have some slides prepared for us this evening to discuss what the RASC does?
I do. Saxon, can you share my part of the screen? Can you see that all right?
We can.
Wonderful. So I like starting all of our public events with a land acknowledgement, but we actually tend to move it to a land and sky acknowledgement because here in Montreal, we are on unceded Indigenous lands, but we share the sky with all the First Nations and Indigenous people from across the world. So these days, a lot of us are looking up, especially looking northward to look towards the Big Dipper, the Little Dipper, to try to see this comet that's passing through that's hasn't come by for 50,000 years and won't come again for another 50,000 years. We're unfortunately with cloudy skies here in Montreal, so it's hard to look up to the north, but every now and then we get a little glimmer of clearness to the west and to the south. So when you do look up, one of the neat things to note is that we are just starting the waxing moon for the snow blinding month. This is the Mi'kmaq Moons project that calls it the snow blinding moon, but the settlers have called it the snow moon or the hunger moon as well, because with the rise of the moon so high in altitude in the nighttime, when it does become full in a few weeks, the light will reflect directly into our eyes and it will blind us. And so that observation is part of this whole idea behind looking at First Nations knowledge and identifying how it matches what we do see in nature and the actual movement of the moon, earth, sun system that we've now recognized and we learn about in introductory astronomy classes. As well, because it's the heart of winter, we see the entire Winter Maker constellation from the Ojibwe in the south throughout the night. And a lot of us love looking at the Orion Nebula and the Horsehead, the Flame, even the Crab Nebula up above Orion. Aldebaran and Taurus leading us to the Pleiades, the hole in the sky, as it's called by a lot of the First Nations people, which is how Turtle Island first came to have Star Woman join us. So when we talk about the night sky and when we look at all of these different objects in the night sky, it's important to remember that we're not the first ones seeing this, and we're not the only ones seeing this. We share it with everyone. Here at the Royal Astronomical Society of Canada, we have centers stretching all across the country from coast to coast. And in the Montreal Center, we've been around for 100 years, the RASC for over 150. Our mission is to really just help Canadians pursue a curiosity, an inspiration about the universe, about everything from astronomy to astrophysics, from stories of the night sky to actually trying to quantify some of the photons coming in from different objects. And at the moment, we're really working hard towards the solar eclipse that's coming up on April 8th, 2024, which will stretch through a large part of Canada, including my own campus at John Abbott College. At the RASC, if you do become a member, you get lots of benefits, including Sky News magazine. You get the Explore the Universe handbook. You have the Observer's handbook, which is world-renowned. There is even an American edition that goes out and is sold through the US. And the Observer handbook is not the only thing that's offered. We have a new Observer's course for visual astronomy, the NOVA program, that's recently been completely revamped. Tomorrow night, our outreach group is going to be providing access to our remote telescope in California to members who are interested in learning how the remote telescope works and doing some observing themselves. And a lot of these images captured by our astrophotographers are shared within a calendar, as well as directly on the covers of the Observer's Handbook, Sky News, and others. For our post-secondary students, our Next Gen committee has put together 2 scholarships, one available for post-secondary study in astronomy or space sciences, and one available for projects that you have an interest in doing within your community, and it's called the Community Leadership Fund. So all RASC members are eligible for any of these different programs. We also have observing programs. Depending on your ability and level, you can choose different types of observing programs. And this became very popular during COVID when we were all stuck at home. But we're finding that a lot of people are really pushing to get these observer certificates. And there's even now an astro imager certificate available for those who like taking a little bit of capturing of the night sky. At the Montreal Center, we have events twice a week. We have a bi-monthly newsletter, Skyward. We have our RASC telescope library and rental set up here at John Abbott College. And our library has an astronomy collection, and we also run events there. And our next event is this Thursday. It's Treasures from the Southern Skies. Our outreach coordinator, Russell Freilich, just came back from New Zealand, and he's going to be sharing with us a little bit of the Southern Hemisphere night skies. And then finally, now that COVID is not over, but at least it's somewhat under control, we're getting back into in-person events. We did a few through the spring and the summer of last year, but we're having a winter event at one of the Vergers La Bonté at Île-Perrot on February 4th, if weather permits, to share the full moon and have some hopefully apple cider and, some good apple pie. So we invite anybody in the Montreal area to join us, and we hope that that if you're interested, you can always reach out to us at RASC Montreal. We also have these wonderful public events, and I'm so glad that when COVID started, Orbax and I kind of connected and started doing these virtual events. Can you believe it's our 3rd one? We've done exoplanets. We've done the celebration of Roberta Bondar being the first woman, and now we're getting out to Mars. This is fantastic.
It's pretty exciting, and it's been a lovely time collaborating with you as well. And I can't urge our followers enough. If you're interested in astronomy, there's only so much that you can do on your own, and there's only so much information that you can get on your own. It really does become trying to observe the night sky in many ways really is a community event. It's something you want to do with people and to share with people. And there's Royal Astronomical Society of Canada centers all over Ontario, all over Canada, really, that you can get involved with if you want to. Of course, our favorite is the Montreal one. However, I mean, depending on if you can't make your way to Montreal every single time, of course, you should look for it within your community to get together with people and take a look up.
Definitely. Always look. And if you need help any month on figuring out what's in the night sky, Orbax publishes these great stargazing guides and even does the wonderful, respectful call out to the First Nations moons. And I love this.
It's been one of the most fun things that I've gotten a chance to do is to work on these stargazing guides and to work with you on it. I mean, working with you is not really that much fun,
No.
but
That's a
working
burden.
on those in general has been lovely. So thank you so much for it.
So I think we've talked enough. Let's bring in our guests now.
Well, exactly. And so, yeah, I mean, that's a good point. We've covered a lot of topics. For those of you who are new to the Guelph Physics live stream, we have covered a variety of things in the past. We actually covered the Perseverance landing live back in 2021. We've covered quantum computing. We've talked about the destruction of black holes and neutron stars and where all of the heavy metals come from in our world. We've talked about batteries. We've covered the whole gamut. And tonight, we're going to discuss actually looking at information from the Martian rover Perseverance and translating that data into something that hopefully any of us would be able to understand, literally discussing what that Martian soil is made of. So without any further ado, let's bring Sal in. Sal, welcome aboard. Now, a lot of these become easier when you unmute yourself. So perfect.
Yeah,
so that would when we first start.
That would probably help, right?
Hello. So Sal, you're
Sal.
You're a master's student in Ralph Gellert's Martian group here at the University of Guelph. What year of your master's are you in? How long have you been studying Mars?
I've just finished my first year. I started fall 2021. And I've been working for a year with Ralph. I'm looking at data from the Pixel rover, and we're primarily looking at soil and rock samples and determining the elemental composition.
Now, for those of you who don't know, Dr. Ralph Gellert's group primarily worked on the APXS, which is a piece of scientific equipment that's sat on the Curiosity rover. And now Sal's working with stuff from Perseverance as well. But I'll let you get into all of that and discuss that whole jumble of everything that's up there on that planet that's only got robots on it. But can you talk to us a little bit about how you came to this? Where did you do your undergraduate work at?
So I did my undergrad here. However, I was in the math department. I did my area of specialization in physics. And in my final year, I had a course with Ralph. It was a radiation interactions course. So a lot of the principles from that course carry over to even some of the stuff that I'll be covering today. We just conference kind of discussed some of the research that Ralph was working on. And he mentioned the opportunity to work with the new rover that landed in 2021, as Orbax was saying. And just to have that opportunity to work on new and exciting data, but that builds on the work that Ralph had done before was a great opportunity for me. So I jumped on board.
Fantastic. Well, that's exciting stuff. And it's always interesting to see that kind of journey and where it leads people. And speaking of journeys, we have a new addition to the team here. Janika McIntosh is joining us this semester as with the social media group here at the Department of Physics at the University of Guelph. So let's bring her on board.
Hi.
Hey, how's it going tonight?
Good.
Well, before we get into a lot of Sal's research, I know that there was some interesting questions that the undergrads had. One of the points of doing these physics live streams is to sort of show our undergraduate students that even though they might be in the depths of studying now, that there are a myriad of pathways after they graduate in terms of finding jobs and of following their passion. Janika, you're going to share with us a unique undergraduate perspective. Do you have any questions for Sal?
Yeah, we were wondering, what has your grad experience been like in terms of how different it is from undergrad?
So for me, it was a bit of an adjustment. Like I said, I've only done a specialization in physics. So that, I took the basic E&M and thermal kind of course, but up until third year only. So I was missing all the quantum and all the statistical mechanics and whatnot. So in my first term, I opted to just do quantum to kind of get my feet kind of wet in the water. And that went well, and the rest of my coursework has gone well. In terms of my area of research, is something really new. I don't have any background in geochemistry at all. But, we've had group meetings collectively, primarily for the past 6 months or so. And, you learn a lot because everyone has different perspectives. Part of my research group includes Adam De Souza and Rafael Caruso, and both of them have worked with Ralph in undergraduate projects. So they've definitely helped me in getting myself acclimated with the terminology and becoming exposed to the array of information that comes at you when you start.
Okay. So did you learn most of the geochemistry that you use now after your undergrad?
Yeah, mostly just through discussions with Ralph. Like, he's a bit of an arsenal of knowledge, to be honest, on that front. So just through the team meetings, there's probably he'll have to repeat things a couple times for them to really seep through. But no, he's been really instructive. And just also reading research articles. This is an area that has a lot of different perspectives. So having the physics perspective, obviously you're lacking the background on the geochemistry, but you also have a bit of a blank canvas, and you don't kind of impose your own views. Especially for this sort of research, there's pretty limited data, so the kind of conclusions you can draw can sometimes get a little bit, I don't know what the word is I'm looking for, but outlandish. And I think the physics kind of grounds you and keeps you fairly honest in what you're discovering, because we're just kind of poking at it blindly,
Bring cream in. Fantastic. Well,
for like how you.
Oh,
Janika, you cut out there.
I think we've hit one of the classic issues that happens in the live stream, the glitching out, which is okay. I mean, although it looks like Kareem's got dial-up there on Mars, Janika is here at the University of Guelph using our UG secure Wi-Fi, which is constantly fraught with difficulties as we stand. So we'll bring her back later into the episode and have her ask some questions that I'm sure they have about the incredible research that you're doing, Sal. But unless I'm mistaken, I guess we should hand the floor over to Sal and let him start his presentation.
Exactly. Let's go.
Cool. Yeah. I think we have a video to show, right?
Oh, right. Yeah. No, sorry. We don't have to Sal yet. Forget about Sal. Let's do a refresh. As I mentioned, we did, so far as I mentioned, we did actually cover the Perseverance landing live in 2021. And I thought it would be an opportune moment to actually show a recap video of what the Perseverance mission was in order to give people an overview before we get into Sal's discussion of the data that he's tackling. So without any further ado, I believe we have a video here from our good friends over at NASA. Saction?
Mars is the closest place that we can reach with robotic exploration that we think had a really good chance of having ancient life.
The Perseverance rover will land at a location called Jezero Crater. Jezero Crater is a very interesting place. It's a crater that once held a lake.
There are a lot of craters on the surface of Mars that could have once hosted ancient lakes, but not every crater that we think had a lake actually preserves evidence that that lake was there.
It had an inflow channel and it had an outflow channel. That means it was filled. The crater was filled with water.
In Jezero, we have probably one of the most beautifully preserved delta deposits on Mars in that crater.
This is a wonderful place to live for microorganisms, and it is also a wonderful place for those microorganisms to be preserved so that we can find them now so many billions of years later.
There is no other place on Mars that has the unique combination of a lake setting, a beautifully preserved delta, and the diverse mineralogy that we have in Jezero Crater. So it's truly a special landing site.
The major goal of the Perseverance mission is to investigate astrobiology on Mars, and in particular, to address the question of whether life ever existed on Mars. The Perseverance rover starts with a design that's very similar to Curiosity, but we've added to it a whole new set of science instruments. And these science instruments were purposefully selected to help us in the search for biosignatures.
We're going to be taking microphones with us. For the first time, we're going to have that human sense on another planet.
Perseverance carries with her a grand experiment in spacefaring technology, a helicopter, the name of which is now Ingenuity.
One of the major upgrades that Perseverance has from Curiosity is that it's able to self-drive for a distance of up to 200 meters per day. As the rover is driving, it's literally building the map of the road it's driving on Mars.
Scientists for years have told us that to really unlock the secrets of Mars, we have to bring samples from Mars back to Earth.
So what Mars 2020 is going to do is to drill samples, put them in small tubes. We're We're going to seal it in its own individual tube. We set them on the surface to provide a target for the second 2 missions, which hopefully will get in development in the next several years and could potentially get the samples back to Earth by 2031.
Perseverance is a very, very profound first step in both our understanding of our place in the universe and a stepping stone towards human exploration on Mars.
Perfect. So as the video kind of outlined better than I possibly could, one of the main objectives of the Perseverance mission is to try to identify potential signs and biosignatures left by microbial life. This is really an extension of the work done before it by Curiosity and in the MSL team and the MER missions. Both of these missions using APXS, which is the instrument that was designed by Dr. Ralph Gellert, who's my supervisor. Both of these instruments concluded fairly conclusively that both craters that they were located at were sites that had once hosted an ancient lake. And even further, Curiosity was able to identify sources of organic material that was left behind at Gill Crater, where it operated, alongside with some sources that would have potentially been energy sources for early microbial life. So the Perseverance mission looks to build upon this further and carries instruments that are specifically designed for analyzing soil samples, not only to determine their chemical composition, but also to determine their bioavailability and how likely it is that these samples possess signatures that would be only present in the existence of microbial life. And as such, the location that was chosen, which is Jezero Crater, as the video mentions before, it's pretty conclusively thought to have been a lake, a large crater that was fed to by a river system. And part of that evidence is through the river deltas, which are basically marks that water leaves on the geology of a planet or in a structure as it passes through it. And it's pretty easy to convince yourself that this was some kind of water flow at some point. About 3 billion years ago, it's predicted that this was filled with water. And the nature of water on the surface of Mars is cyclical. So it's thought to have gone through a sequence of wet periods and dry periods. And the idea here is that Jezero was flooded during one of these wet periods. And as such, possesses a lot of the characteristics that would not only have hosted ancient life at some point, but would also preserve it today. And I think one of the important things to keep in mind is that these missions are obviously chosen location-wise based on the characteristics of the location, and as such, they're fairly sparse. And the video mentions that the rover covers about 200 meters per day, has a top speed of about 0.1 kilometers per hour. So the idea of reproducing data is practically impossible, and we need to make sure that what we're putting on the planet and the instruments that we're using are innovative enough to pick up on these determinants and signs for microorganisms, but are also reliable enough and can be tested, or we have some measure of the reliability of the results that we produce. So to look a little bit more closely at the Perseverance rover and how it's equipped to carry out this sort of analysis, there are basically 4 major components that are responsible for analyzing rock samples, where 2 of them are the major instruments that are actually carrying out the chemical analysis of these samples. So starting from the top, the big camera at the top that's mounted on the mast that you can see here is named SuperCam, and this is essentially a remote sensing instrument. It can measure the composition of rocks at a distance of up to 20 feet, and it does so on a bulk scale. So it can measure the composition of a rock, but doesn't have the sort of fine scale measurements that we need in order to find signs of like biosignatures left by the microorganisms on the planet. And the idea here is that this instrument allows us to potentially conserve a little bit of time. As I said, the rover won't cover much distance, so overcommitting to moving the rover to a location for further analysis. Here we have the ability to look at that ahead of time in a little bit of detail to identify potential interesting sources. Following through, we have the Mastcam system, and this is a system of stereoscopic and panoramic cameras. So it takes a bunch of pictures that we've likely seen published in the media. The Sherlock and Watson system is very specifically designed to determine not only the chemical alterations that microbial life would have left on the geology of the planet, but also measure that at a much finer scale as it relates to the structures of the material. So as these microbes exist on a soil sample, they not only alter the chemical composition, but they also alter the structure and the texture of the material. And this is a very important aspect that was missing in previous missions to be able to detect these signs of life. And the topic of today's discussion will be PIXL, which is the instrument that I'm gathering data from. This is an XRF spectrometer, which I will explain a little bit what XRF means and how that works. And it's able to carry out similar experiments as APXS before it, but it does so at a much finer scale. So it operates at a micro scale. These micro scale observations, both of the, as I mentioned before, the structure and chemical changes in the composition, are essential for determining signs of biosignatures left on soil samples. So looking at what came before it and what basically the principles behind the instrument, APXS was a predecessor that, as I mentioned before, was used by the Curiosity rover to establish this idea that liquid water existed on the surface of Mars, and particularly that the conditions for life were present. It was not only used by the Curiosity rover, but also by the MER missions before it, and the Mars 96 mission as well, and several lunar and asteroid rovers also employed it. The idea is that it's very similar to PIXL, where it uses X-rays to analyze the target, but it also has the ability, because it has a radioactive source of curium, it'll decay and produce an alpha particle. And this alpha particle will interact with the atoms of the sample to measure the mass. We can, because the alpha particle is essentially a helium atom, which is 2 protons and 2 neutrons, has a large cross section. So when it interacts with atoms from the target material, it will collide similar to a billiard ball. So by conservation of energy and angular momentum, we can determine based on the incident angle what it collided with. So that's an ability that APXS had that is not present in PIXL. The similarities, though, is the XRF spectroscopy, which this determines the chemical composition of the rock sample. And looking at it in a little bit more detail, I thought it was important to outline a schematic, as APX or PIXL will work through a similar principle. The diagram is a little bit clouded, cluttered, but the important things to take away is that we essentially have an X-ray optical that will focus on the specific point on the target, and the detector head has a series of detectors that can pick up incoming X-rays. As the X-rays strike the target, they carry out excitations that produce fluorescent X-rays, which I will cover in a second in more detail. But as we set the detectors to the target, these will pick up the fluorescent X-rays and can tell you a little bit about the composition of the sample. And the idea is that PIXL will do this in a very similar way, but we'll do it with a much higher level of precision. So as I mentioned, the area that PIXL will operate over is in the micron scale, whereas APXS focus on an area about a centimeter, in the scale of a centimeter. So we acquire a much more precise picture. And as I mentioned extensively, this is necessary for when we're studying the changes in the chemical composition at this small scale. We can also use other pieces of equipment on board PIXL to study the changes in changes in chemical composition to changes in the structure. So to understand the physics a little bit here, I keep mentioning XRF, and this is a process that basically occurs when a target atom becomes excited by an incoming X-ray. The idea is that when the X-ray comes it's focused onto a target, it will penetrate quite deeply into the atom because of its low cross section, and potentially cause excitations in the K shell of the electron or the atom, which is the innermost shell of the atom. And when this collision will likely strike an electron because of the high density in the electron cloud compared to the size of the nucleus. And this will essentially transfer some of the energy, or the energy of the X-ray, to the electron, which will become excited. And this excitation pushes it up an electron shell. If we think about the Coulomb potential between the nucleus and the electrons are being forced. There's a force acting on them towards the nucleus. So higher energy shells require more energy to be maintained. As this electron jumps to a higher energy shell because of its increase in energy, this vacancy creates an unstable condition for the atom, which it tries to counteract by pushing an electron from an outer shell to an inner shell. And when this happens, as I mentioned, the Coulomb force is stronger the further out you are from the nucleus, because you have more of an influence from the Coulombic force. The idea is that this difference in energy will be expelled by the atom in the form of an X-ray. And this is the fluorescent X-ray. So depending on which energy shell fills the vacancy, as well as where the vacancy was created, the chances of the vacancy, the probability is that the vacancy will be created in the K shell, but it could still be created in an L shell. So that will determine a characteristic energy that the X-ray will be fluoresced at. And by turning on our spectrometer at a specific point in time when we're doing this, we can determine what element these X-rays are being produced by, because the difference in energy shells is characteristic to each atom. So the idea is that by studying these fluorescent X-rays, we essentially create a fingerprint for what sort of atoms are present in this material. One thing to keep in mind is that a competing process would be if, particularly for lower Z elements, so smaller atoms, when this energy from the X-ray is transmitted onto the inner shell electron, the atom might choose to instead expel an outer shell electron to counteract the difference in, instead of filling the vacancy, it will instead expel an electron. And when this happens, we don't get an X-ray that we pick up, making our detection, setting limits on our detection capabilities, essentially. And this really only occurs for low Z elements because of the fact that they don't have as many energy shells to fill. If an atom is smaller, that means it has less protons in its nucleus, so consequently have fewer electrons, meaning that that arrangement might be more favorable. And this poses a limit in what we can detect. But this all comes together. We can see it in the following picture. This is a typical XRF spectrum. And the characteristic sort of shape that it has is specific to these XRF excitations. It's called a Bremsstrahlung peak, which is this hump that we see that almost looks like a Gaussian, but it's offset to the left a little bit. So if the sample was like a Teflon sample and didn't produce any spectra, what we would see is just the characteristic hump without any of the peaks in this region. In the following picture, it's the same picture, but just zoomed in with more detail. Essentially, as I mentioned before, the energy of the outgoing X-ray is characteristic to each element because of the difference in energy shells, which is specific to that element. So this data has been tabulated, and it's well known through experimentation. And what we can do is once we produce this spectrum through our detector, we can essentially, by understanding the position of these peaks and determining their peak area, we can determine the elemental abundance inside of that sample. So this is the basics of the physics that goes on in actually carrying out XRF with our detectors. And, this sort of thing is done in geology extensively. And like I mentioned, it was done by the Curiosity rover and now Perseverance, and other missions before them. But this isn't exclusive to geology. It's an area of spectrometry that is carried out in many fields. And an interesting application was carried out in an anthropological journal here, where they analyzed a painting from 1454, 15th century painting. And it's a famous painting by some famous painter that I don't know. The idea is that looking at the composition of the paint, they could make certain claims about the society as a whole at that period in time. So, for example, in the Apostles' Carnation, they were able to find a certain arrangement of elements, which suggested that the copper, it had the use of ochre and vermilion and lead white. This could have implications on the sort of social standings and trade relations that civilization might have had, for example. So it's just a cool application of XRF. You can see it applies to, the physics applies to many different fields. So looking at Pixel, again, in a little bit more detail, the idea is that by using an XRF detector, we can potentially carry out some kind of site-to-site comparison of the Martian geology. As I showed in the picture before, the rovers are fairly far apart, at least in the scale at which they travel. And Pixel does this by using an X-ray that is 120 microns in size. This is about the size of a grain of sand. And as I mentioned before, this allows us to understand the chemical composition of a given sample at a very, very fine scale. And the idea is to use these changes in the chemical composition alongside the Pixel is equipped with a camera. The idea would be to be able to correlate the changes in the chemical composition along with changes in the texture that are seen in these images. But in order to do this, we need to have some kind of mapping that relates our spectra to the picture that we're taking. So this instrument is equipped with a series of lasers and camera systems that essentially are able to point on the target and determine the spatial position of the target, and then relate it to an actual image, pixel by pixel, and that's not no pun intended there. It genuinely means like a pixel image. You're able to actually create a pixel coordinate. So you can relate what you've seen in a given spectrum, like the one I showed before, back to the image that you have. And in this way, geologists and astrobiologists can make specific determinations on the bioavailability or the sort of preservation of biosignatures on a sample. And this goes even further, not only to understand these chemical compositions, but it might actually give us a bit of an insight on the spatial distribution. So this would be a little bit of insight on the crystalline structure of this given sample. And the idea here is to use these microscale observations that are done by Pixel, along with some of the macro scale observations like that of SuperCam that I mentioned before. And basically, as we can see from this picture here, the Pixel instrument is comprised of three major components. Most of the science is done by the sensory assembly, which is what focuses and generates, focuses, and detects the X-rays, as well as creates these mappings and images that I mentioned. Another important element, though, is the electronics unit. The body of the rover is what's called, I believe, warm electronics, something like that. The idea is that some electrical components need to be shielded from the high amount of cosmic radiation that's present in Mars, because it doesn't have a magnetic field, or a strong magnetic field at least. Cosmic radiation is constantly bombarding the surface, and this can fry your electronics. So those need to be protected and are connected to the sensory assembly by a sequence of wires. The idea here is that Pixel is mostly working autonomously, so it will send data back to scientists here on Earth, and they will analyze the data and determine at a very broad level. But that analysis will allow them to determine the next steps, and they will send a sequence of commands to the rover, which then relays this to Pixel itself, and then Pixel will operate semi-autonomously in that way. So the body unit electronics is responsible for receiving this information from the main computing system in the rover and relaying it to the sensory assembly. And lastly, what we have is the Pixel calibration target. This is used for calibrating not only the actual X-ray generation and focusing system, but also for the camera and the hyperspectral mappings that I keep discussing. And this is a look of them more closely. So the sensory assembly, which is kind of the meat and potatoes of the instrument, is about the size of a lunchbox and is about 10 pounds. And this is mounted on the armed turret. The calibration target we can see here at the bottom, and the electronics, as I mentioned, are housed inside of the rover. And in this image, I just wanted to include it to kind of draw a parallel to the schematic I showed of APXS before it. We see a lot of similarities where we have some kind of optic that will focus our X-ray. And then in this particular instrument, we have 2 detectors. This is both for the sake of redundancy, but also to measure potential Compton effects that can occur. There's some potential that with some degree of probability, there might be preferential processes that occur, and this would cause for the X-ray to be deflected in one of the detectors and not the other. So if we were to pick that up, that would be a potential signature for those kinds of processes occurring. The MCC and SLI system that we see on the rover head here, or the assembly head here, those are basically what creates those hyperspectral maps I keep talking about. And we'll look at that in more further detail in a second. Actually, right now. So this is basically an example of how these spectral maps are done. The idea is that each point on the map B here that we see, the 3D axis, each one of those points relates to one of the spectra, similar to the one I showed before. In fact, the spectrum that I showed before is for this calibration. It's just specifically one calibration target rather than the entire calibration target. The idea is that each one of these would, each spectra would have a positional vector that's an XYZ coordinate, and it would relate to one of the points that we see on the mapping there in image B. But we can use the images that Pixel is actually going to produce to then relate these mapping points to the locations on the picture. So this is basically how the instrument would do that in a real example. So now that we understand a little bit about how the rover operates and or how Pixel in specific operates, how does this relate to the interpretation of data? How can we actually draw results from data? And the idea here is that for a given sample, a few thousands of spectra might be composed. Often for the calibration target, as an example, there might only be about 100. We saw about maybe 100 points here. But for any given spectra that's of interest, chances are there's going to be at least 1,000 to tens of thousands of spectra. And as I mentioned before, each one of these spectra has a positional vector associated with it that allows us to relate it to the position in 3D space, and then later to the image that's produced. The idea is that, back to the spectrum that I showed before, back here, each one of these peaks, as I mentioned, corresponds to a specific element. And the area under the peak, subtracting the background, which is characteristic of XRF, but that area minus the background would essentially comprise the elemental abundance. So by measuring these peak areas, we can yield the elemental abundances. And what we can do is now, once we've carried out that preliminary stage of analysis, we can then compare these elemental abundances or elemental ratios. So now we're dealing with the ratios between different elemental abundances to define specific mineral compositions that might be present. And these different elemental abundances will suggest different compositions, as I mentioned, but also structures. So depending on the sort of minerals that we'll see, the sort of crystalline structures that can be produced will change. And in order to understand this in a little bit more detail, I think I should just give a little bit of an example as how this is done at a geochemical level. Particularly, my research is currently focused on looking at iron and manganese for the spectra produced by Pixel. And the idea here is that when we have a rock that hasn't been altered by any water, it's never seen a drop of water, these rocks are produced through some magmatic process, just like they are here on Earth, and they get expelled, let's say, through a volcano or a crack in the crust of the planet. These will cool and form a rock, and let's just say that this rock has never been abraded or seen a drop of water or chemical alteration. The idea here is that iron and manganese, if we look ahead at a periodic table, we see that they're neighbors in the periodic table, meaning that their atomic number is similar. And in these igneous rocks, they typically exist as iron 2 and manganese 2 when they haven't been oxidized by the presence of water. And it's important here to note that both of these elements have a relative ionic radius. And in the figure here, we can see this is a complicated crystalline structure. The example here, I believe, is pyroxene. And the idea is that the green symbols that we see are most likely silicates. So that's kind of the basic building block of a rock is silicate. The typical rock that we would think of is, for example, quartz, would just be an arrangement of those crystalline structures. Different permutations of it exist, though, and in this specific one, we would have some element, which for our purposes, we can think to be iron in the teal in the conglomerates in the center there. And the idea is that because of the similar ionic radius between iron 2 and manganese 2 is found at a lower abundance. That's due to the production in stars. So in our solar system, I believe the ratio is around 50-1. Iron is just a more stable when it's produced in nucleosynthesis, so it's more abundant in just throughout the solar system. But the idea is that in trace amounts, manganese is found again throughout the solar system, and in a given structure, it can actually substitute for iron when they're in this form. So to recap, basically an igneous rock, we would have a certain amount of iron that can be substituted by manganese readily. And this ratio between them and how often manganese is substituting in is fixed for each planet. I believe it has to do with the abundance on that given planet. So for example, here on Earth, the ratio might be 30, on the moon, the ratio might be 40, and on Mars, the ratio is around 50. For some typical igneous materials like olivine, pyroxene, and augite, we see that the ratio will, on average, if we have an even distribution of the three and other ones, sit somewhere around 50. So this means that we have 50 times as much iron as we do manganese. However, when we're dealing with a sample that is now, we're not talking about an igneous rock, it has been altered by some kind of process. So let's just say in the case of Gale Crater, it has been abraded by the flow of water, and that water has been able to penetrate beneath the surface and interact with the internal chemical composition. We expect that oxidative processes would occur. We know that iron will oxidize, and this, if we remember some of the chemical schemes that it can do so, like the ones I've outlined here, it will oxidize typically to iron 3. And once this happens, the ionic radius of this atom is vastly different, and these alterations will basically alter the ratio that we observe. I mentioned before that the typical ratio is about 50. The alteration would increase the amount of iron 3, and in many cases, like is the case in olivine, for example, this would change the structure that we see here. It would be a different sort of arrangement of molecules, and the idea now is that manganese is no longer viable. It can no longer substitute for iron the way it did in an igneous rock, and instead it's going to be leached out. So we're going to have some manganese oxide that's leached out of the sample, and this will force our ratio of iron over manganese to be higher. So the basic concept here is that we can use this iron over manganese ratio as an early indicator of chemical alteration, and the type of iron that's found will change the sort of elements that we can this is sort of mineral combinations that we can form. And one way that this can come together is in the following study. I just give an example of something that I'm after in my research personally. Again, as I mentioned, this fluctuation in iron over manganese will suggest the idea of alteration. And once we've established a basis for these values of iron over manganese for all the spectra, we can look at other elements in more detail. So the example that I've outlined here is sulfur. The idea is that sulfates, so oxygen is ubiquitous. It's found in every rock in high concentrations. So whenever we measure an element, we can assume that it's found as an oxide. So if we measure some sulfur, we expect that this is going to be in the form of a sulfate, which is SO4. And this has a net charge of -2, I believe. And when this is found, as in the plot here, we see that in the x-axis, this is iron over manganese, and it's increasing. So on the farther end, we have that case where manganese has leached out of the sample, and we have a higher concentration of iron, suggesting a concentration of iron 3. And this would be supplemented by our discovery if we were to find this sort of trend, because we see that sulfur increases as iron increases. The increase in iron suggests an excess of iron 3, and as such, we could have compounds such as ferric sulfide being produced. And the reason why this is interesting is because I mentioned before the idea of being able to do site-and-site comparisons using XRF data. And previous missions like Curiosity and the MER mission, I believe Pathfinder as well, have analyzed dust quite extensively, which Pixel looks not to do. So Pixel is actually equipped with a series of brushes before carrying out the analysis. And it's supposed to be essentially shooting its X-ray at a clean sample. But the idea why dust is interesting is that because it's kind of the smallest constituent, or the smallest form of minerals that we can really find, these are fairly ubiquitous. They should be homogenized throughout the planet. And as such, they get blown by wind and will cover the planet pretty much the same at every location. So even though the rovers are really far apart, what we should measure in the dust should be consistent at Gale Crater and at Jezero by Perseverance. So the idea is that if we were to find a sample that possessed no dust, this sort of arrangement where an increase in iron over manganese would go with an increase in sulfur would be seen. So if we are to analyze the spectra and we see that for majority of the spectra, there is no trend between iron over manganese, and we see this sort of behavior, that would suggest that that's not dust and it's actually a bona fide sample on the planet, and the dust cleaning worked as intended. However, if for specific points, and remember we can create these 3D mappings and relate them to the image, if for a specific point our ratio suddenly drops back to near 50, where it was much higher, and we don't see this sort of trend between sulfur and chlorine, that would be the case that we would expect in dust. We would expect that dust would be the most typical sample that we would find on the planet, which has a ratio of about 50, and these sorts of trends aren't present. So by doing an extensive analysis of the samples produced, and by looking at these sorts of elemental trends along with other ones, one can then go and look at this MCC data, looking at the positional vector for each spectra to try to identify dust accumulates. And the reason why this would be a big deal is because it allows us to do side-by-side comparison of Pixel, APXS, and Curiosity and in previous missions. And this could help us in supplementing the discoveries both by Pixel using APXS data and vice versa. Each instrument will naturally possess specific properties that will make it better at analyzing specific elements. So for example, Pixel, because of its high grade of accuracy in focusing the laser, is theorized to perform better when analyzing sulfur. So in theory, one thing that could be done through this sort of analysis that I'm doing is help to supplement some of the APXS calibration standards, perhaps, or at least understand some of the results that were carried out in the past with a higher degree of accuracy. And that basically outlines my core objectives here. Just to kind of wrap it up, basically the laundry list would be to first find an iron over manganese ratio for all the thousands of spectra produced. Once this ratio is obtained, it's kind of like a first sift. We can then look at other elemental abundances and ratios and do that sort of comparison that I showed in the previous plot. An interesting thing would be to find and identify potential dust candidate samples that then we can compare between the two missions. And additionally, we could produce a basis for comparing Pixel results not only to the previous missions as I discussed, but also to the instruments that are on board Perseverance. So SuperCam is one that I mentioned, and one of my lab partners, Raphael, is working at looking at manganese with SuperCam. So once these preliminary searches have been done, an interesting thing would be for us to be able to cross-reference our results, particularly for manganese, mostly for ensuring the quality of the results produced. Curiosity did this extensively, where ChemCam and APXS worked in conjunction to raise the validity of each other's results. So that would be an interesting thing to do. And that basically wraps up most of my presentation. The rest of my material is basically for appending to any questions that might come up.
Fantastic. Thanks, Sal. This is really exciting and interesting work. Kareem, there's been questions popping up through the various different streams. I wanted to know, Kareem, do you have any questions on the RASC end that were popping up, so our viewers have been asking?
So we had one. We actually had a recent discussion about, about looking at some of the craters in Labrador and on other areas for training for the Artemis mission. And somebody was asking if there's areas in Canada where you have been able to do similar analysis, or where you know that similar analysis has been done by Pixel-like instruments to compare to what you're trying to see in Mars.
Yeah, that's a great question. So XRF, and these are particularly interesting for planetary exploration because they're very small scale. They're very compact instruments, and they're also very reliable. So as I mentioned, they've been used dating, I think, all the way back to 96 with a high degree of accuracy. Typically for geology here on Earth, these are sometimes used when we go to remote locations because of the size constraints, but typically you have the luxury of being able to take a sample, bring it back to the lab, and analyze it with a high degree of accuracy. That's kind of been outlined by the intro video, where they mentioned the future ambition is to bring back samples to Earth, right?
We'll 8 years, we can wait that long.
Yeah, we'll see if it's, what multiple of 8 it ends up actually being. But
Sal, you're breaking my heart.
I do know that actually one paper that I actually had on the presentation but removed for the sake of brevity was that XRF was used in Australia. So I imagine similar things are being done in Canada at a very remote location to determine the composition. I believe, don't quote me on this because I'm not a geologist, but I believe to be able to supplement some of the dating techniques that were used for the formation of strata. So that idea is definitely what scientists are looking to do, to be able to, like, for example, the calibration target that I showed, if we want to pull that up again, one of the components here is BHVO should be the upper left. So it's this gray sample here. BHVO is essentially like the most standard basaltic rock that you can find on Earth. And what they did is they ground it and put it in glass so that it would survive the journey to Mars. But this is very similar to what the question is suggesting, that we want to compare what we find on Mars to an expected thing here on Earth. And that's what essentially the calibration of the system is.
Okay, awesome.
Exciting. There's a couple of questions that have popped up in the chat from a Julian Fernandez. I don't know if there's any sort of relationship there. But let's start off with the first one, which is an interesting question. The previous work done with Curiosity and in your group has been with the APXS. What's Pixel showing us that's different than what the APXS was showing us?
So one of the things I mentioned was the higher resolution for elements like sulfur. So sulfur is a low Z element if we look at a periodic table. And as I mentioned, the XRF is one of the competing processes is this expulsion of an electron, producing an Auger electron. When this happens, we don't detect anything from our sample. Sulfur has been something that was talked about a lot in the implementation of Pixel. And one of the hopes is to, as I mentioned, through this discovery of the dust, would be to supplement some of the data that APXS has. Unfortunately, though, at this point, not much analysis has been done by the Pixel team, or published at least. The most recent data dump included some oxide concentrations. So that has been the first data dump that has been done, and it's a very preliminary view. Essentially, doing what I showed before, finding those elemental compositions, finding peak values for a bunch of the different samples that were looked at, and these are just oxide concentrations because, as I mentioned before, oxygen is very ubiquitous. So anything you find, you assume that exists as an oxide.
Let's bring in Danica here as well. I'm sure there's quite a few questions, especially from the undergrad perspective on the work that you're doing. Yep. There we go. Hey, Janika, how'd you enjoy the talk?
Hey, it was great. Some of the undergraduates here just have a fun question as well. Wondering, with the talk of finding signs of water, if you think it's hopeful to find fossilized remains of life on Mars?
No, I do not. Because this life was theorized to have been microbial. And that, I'm not the best person to talk about this because I'm not an archaeologist. But as I understand it, these types of, when we identify such ancient life here on Earth, like we're talking billions of years ago, like early, very early life, we can't actually, for a lot of these cases, we actually don't have rocks that are that old. But what is left behind is the imprint on a soil sample that is characteristic to life. And I believe that's how they find microbes or determine the age of microbes, is by not a fossil itself, but the sort of distinct features that it leaves on a sample, on a given piece of soil. And that's the idea here with Perseverance, is to actually find these micro scale changes in the structure that are only characteristic to microbes, to very small and very primitive forms of life. The complication here is that you need to do, you want a multi-pronged approach where you're looking at chemical fluctuations and also these changes in the structure. But in terms of an actual fossil, at least based on what I know, no.
Well, I mean, most of the Martian fossils, if correct me if I'm wrong, I know you're not an archaeologist, but I know that most of the Martian fossils are in the Martian museums. And my understanding is that those are on the other side of the planet from where we keep landing.
They're over near the South Pole, yeah.
Right, yeah.
I think that's accurate. I believe that's accurate.
And I mean, they're only typically the hours are terrible. I think it's like 2 to 4 from like Tuesday, Wednesday,
not ideal.
Thursday or something. Yeah, so it's not ideal. Janika, is there any other questions that you might happen to have?
Yeah, another fun one from the undergraduate says, do you think that we can terraform the planet Mars and perhaps even rebuild the atmosphere into a more Earth-like environment?
Yeah, that's a good question. So
it's
I did hear,
because that type of topic has come up quite a bit lately, especially with continuing environmental concerns about Earth, right?
Yeah.
This whole idea of having a plan B or a planet B. Yeah, that's a great question. What are the realities of that kind of thing happening? You're a second-year master's student. You must know.
I have to know, right? It's part of my credentials. Otherwise, I don't get my degree. Yeah, I think also when Elon Musk tweeted something like, let's just send nukes up there, everyone got pretty excited. He seems to be someone people rally behind. But actually, I'm not an expert in this. This would be maybe a question for like a petrologist or something like that. But I had actually read a study that, so the idea is that the polar caps house a bunch of CO2, right? It's instead of being frozen water, it's actually frozen CO2. And there's a significant amount of CO2 on the soil itself, actually. In fact, MOXIE, which was one of the instruments that I showed, it's the first instrument that can convert CO2 to oxygen. So there's an abundance of CO2 for sure. But I had read some kind of study that analyzed the abundance of CO2 and measured that, the Martian atmosphere is about 1% of Earth, potentially even less than that. And that even expelling all the CO2 in every rock and all the CO2 in the polar caps, you might attain 5%. So the idea of having Earth 2.0 seems far-fetched. I feel like I keep shooting down all your cool ideas. I'm a bummer here.
But I mean, there is probably quite a stark reality, especially depending on the success of the Artemis missions coming up, of actually going and doing Martian camps or base camps on Mars with the potential of an orbiting space station. Mm-hmm. So while terraforming is probably quite a far ways off, I'm not sure what year Star Trek II set that up to be, but I don't know. Kareem, what are your inputs on this type of thing? I mean, it's been picked up by the media. It runs around in these sort of cycles all the time. What is the possibility of humans living off-world? Where do you see this going?
Well, one of the big realities, unfortunately, with Mars is there's not enough of a magnetosphere to protect it from solar radiation, from cosmic radiation. So even if we were able to find some way to enhance the atmosphere, it wouldn't last. And that's the same. I mean, the different problem with the moon is that there's no atmosphere, but with Mars, the atmosphere itself just keeps getting irradiated away. And so trying to set up some sort of a future home as Orbax, I mean, I get he wants a retirement spot, but It might be a little bit far-fetched, and
you got to change those hours in the museums. I'm not showing up between 2 and 4 on Tuesdays and Wednesdays.
But it's an unfortunate reality that we really are the most hospitable place in the solar system that we've identified so far, and the moons of some of the outer giants might be a better location to look at rather than looking at other planets within the solar system.
Yeah, it's an interesting point. I'd also like to point out that we're chatting amongst ourselves, but if you viewers out there have some questions that you want to ask, put them in the chats and we'll pull them up on the screen. We have questions for Sal, questions for Janika, or for Kareem or I, just even about astrophysics, physics in general, and whatnot. Otherwise, we'll head towards wrapping this up in the next 10 minutes or so, unless there's more questions coming through. I did see a question in here, which was an interesting one, which I think it's actually something that I was kind of curious about myself. Just the mechanics is all. Again, this comes from our friend Julian. And this question is this. Is the analysis only on surface samples, or are they drilling and taking samples from inside the soil? We see all this media footage and talk about these drilled samples, these collection samples, and their eventual return to Earth. But the pixel data itself is just scanning the dust on the surface. Or how deep is that scan?
X-rays penetrate fairly deeply into a sample. They have a low cross-section. So you expect that the penetration depth is going to be fairly significant. Ideally not picking up the dust, because like I mentioned before, dust should be uniform. So those would be results that wouldn't be too useful. I do know that the drilling does occur on the cached samples.
Yeah.
So they're over, I think there was a video earlier. It basically drills onto a sample and can pull it into essentially the body of the rover and caches them with the eventual hope of returning these samples to Earth. But there's also RIMFAX, I believe it's called, which is an instrument that's used for larger scale geology, and this looking for seismic activity.
So actually, bring up this schematic. I believe we have the schematic of Perseverance here with us. If Saxon can pull it up, there we go. Does that help you? So there's RIMFAX, the subsurface radar.
There's RIMFAX. It's basically a radar that's looking at seismic activity underneath the surface. But in terms of the sort of, the biomarkers or biosignatures left by ancient life, they would be within the strata that's at the top of the surface. I think digging further could potentially give information, but unfortunately this isn't something that the rover's equipped to do besides drilling samples.
It's interesting, especially we're collecting such a cross section of data and information, all the various ways that we're collecting these samples. Here we go. Well, we have a question from one of our viewers. I was just going to continue to speak and vamp about whatever. It's unimportant, my ideas. Harold Locke's here. It seems that industrial expansion and the settlement of plants will be the first forays of Earth. Unfortunately, that commentary seems to really be in the foreground here, that people will just be looking at as places to go and to mine.
Yeah, people want to go on vacation, right?
Well, not even that, just in terms of trying to we've done such a great job of managing our natural resources. I'm sure sending ships into space to pull them off of others is there.
That's even the whole attraction of the Psyche mission, right? Is bringing
exactly.
Yeah.
You can speak to that, Kareem. Go ahead.
Well, no, it's just the heavy mineral presence in some of the asteroids and trying to see if there's a way to get some of those metals and bring them to Earth to use them. Not just the gold that people want to hoard, but actually some of the rare metals that we can use in technology that we are developing that we don't have enough natural resources for the amount of applications that we would have of these technologies.
Yeah, it really brings up a lot of ethical and moral questions that go along with the idea of space as business rather than just as scientific exploration. And I think as we see this billionaire space race continue to heat up, I don't see that dropping off anytime soon. We're really going to be confronted with the realities of who will we trust with the universe's resources or the solar system's resources.
We have that now with the discussion of whether or not it'll be first private bases or which country will have a base on the moon first and when the human presence will be there, whether it really will be Artemis 3 that's the first one back there, or if China will get there first, and what that will mean in terms of the access to different areas on the moon. And it's kind of a shame that that's the way the discussion has to go, but that's the way it started, right? With the Cold War and with the space race between the US and Russia. And The rest of the countries like us in Canada, we were a support network, but it took a while for us to have our own footprint, and it's not an independent footprint. Even the missions with the European Space Agency or with JAXA or with any of the other countries, very few countries are doing things solo on their own that are successful. You have China, you have UAE that had a couple, you had Israel that tried their mission to the moon, India got to Mars, but really, if there was collaborative effort out there, who knows how far we would have gotten by now.
Well, that becomes one of the most inspiring and the most upsetting things I think about space exploration is that, beyond any of the other sort of fields of science, I find that space unifies so many people and brings together so many scientists across the globe to create these incredible machines of scientific discovery that we send to the stars. However, at the same time, nothing's stopping anybody else from trying and doing it on their own, right? So it's we've wandered down a strange moral and ethical slope here that our live streams don't usually touch upon. So Sal, thank you for bringing that to us.
But I am going to point out that there's the whole field of citizen science where even if you're not a master's student or a PhD student in the group, you can still contribute to space exploration. This image behind me was processed by Pete Williamson from the UK, and he has processed images before, and a lot of amateur scientists and just astrophotographers who just love dabbling in this find things like dust devils that give an explanation of what you see from rover data that wasn't seen when they first looked at these images. Because there's just so much data coming in from the rovers, there's more than a set of grad students can do. Even if Sal sacrifices all his sleep and doesn't eat and just sits there and works on he still won't get through.
I won't even make it then.
No, exactly.
Well, you find that in all fields of science, physics and all sciences, the lesser sciences, with this whole concept of we've reached a point where we collect so much data now that you don't have the human hours to actually go through it, sift through it, and pull information out. How much, and I mean, this is open to the panel, and I don't know whether anybody can answer this, but how much of this is being done by AI these days, or what is the look forward to having machine learning and AI parse through this information on our behalf?
They're starting to train a lot of AI algorithms. So, for example, galaxy images taken from observatories.
And like the phone, like this one?
No, actual galaxy images. But just classifying galaxies requires an AI to get trained constantly.
Right.
And so Zooniverse has these programs where individuals like us can just go on and make these classifications, and then they train the AI based on the standard of classification a human eye would give, and they do that iteratively to make that AI smarter and smarter until they can do it themselves.
Yeah, I mean, I think that's what we're probably going to have to see moving forward, right? The only way
they even do that with trying to detect supernovae or exoplanet transits. Is they have AI try to identify when a dip is significant enough that you have to look at it again.
Mm-hmm. Yeah, exciting stuff. Well, I mean, I think we're probably getting close to wrapping this up.
I think so. Yeah.
If there's any further questions that are come rolling through, Janika, do you have? We'll give the viewers a chance to post any of their last minute questions. But Janika, do you have anything to take us through?
Yeah, I mean, we were wondering since it's so hard to make Mars like Earth, what attempts is Perseverance making to bring Earth-like conditions to Mars instead?
That's a good question. Earth-like conditions to Mars.
That might be the instrument that's trying to create oxygen, right? Trying to actually.
Yeah, that's true. Yeah. Yeah, MOXIE is, as I mentioned before, it's the instrument that's actually producing oxygen. I think this is kind of a test run, similar with Ingenuity, right? It was a test run to see if it could even be done to kind of promote the Artemis missions, for sure.
I have to say, Ingenuity is just
quite small, right? Is there room for improvement that's going on right now for that?
Sorry, what was the question?
The MOXIE machine, it's quite small, right? Is there some room for efficient improvement going on right now?
Yeah, for sure. Like the MOXIE use, if I understand correctly, it's essentially just a prototype. It's just a test model. The reason why it's small is because it when they're selecting what instruments to put on this, everyone gets a hierarchy in the list. And that, unfortunately, as I mentioned, the primary objective of the mission was to find potential signs of life. So that, unfortunately, doesn't contribute to that point. But they wanted to include it as the Artemis missions, and the idea of putting humans on Mars actually picks up. You can't carry that much oxygen with you, for sure.
For sure.
Yeah.
All right, then. Well, I guess I'll give our panel an opportunity to plug anything. Janika will be joining us hopefully on future Guelph Physics live streams. We've started again this semester, and the intent is to go through monthly. So if you're watching us now, please take a moment to subscribe, and we'll see some of these monthly physics live stream updates if you're joining us from the RASC chapters. Janika, anything to plug?
No.
All right. Well, thanks for joining us tonight, Janika. We'll say goodbye to you later. Sal, where do people find out about your research, or where can people see more about Pixel?
Yeah, so the link beneath is Ralph's personal page. So it'll be all the IPXS information, basically all his work and that of his graduate students. For me specifically, I think my email was included. So if you have any questions, you can definitely shoot me an email.
Sure, we'll put that in the description below in the YouTube page, so that if anybody's trying to get in contact with you after the fact or is interested in following up with your research,
absolutely,
you directly.
For sure, yeah. And even if it's not related to Pixel specifically, if you just have questions about kind of my journey in science and through grad school, I'm happy to help for sure.
Fantastic. Thank you, Sal. Kareem, the Royal Astronomical Society of Canada in general, or the Montreal chapter, how do we find you? How do we follow? How do we see all the incredible work that you're continuing to do?
So the Montreal Center, you can visit our website, raskmontreal.org/Titan, and you can feel free to email any of us, ask us questions, join us, please. We have members from all over the world, actually. We don't just have members in the Montreal area. We have some that join us virtually for our clubhouses on Zoom, for our public events that we have monthly. And if you're interested in volunteering to be part of any of these public events or share some of the work that you're doing, if you're in the audience, or if you have ideas on public events you'd like to see, maybe for the 4th annual co-presentation between Guelph Physics and Rask Montreal Center next January, feel free to shoot us a line and let us know your suggestions. We're always open to ideas. And you can also catch me weekly, hopefully soon again, on Space Oddities on Mondays and on the Global Star Parties on Tuesday nights.
Fantastic. And if those of you joining us from the Guelph Physics side, please make sure you go and give the RASC Montreal YouTube channel a follow so you can stay in touch with what they're doing.
And same thing, vice versa. Everybody who's watching us from YouTube/Rask Montreal, go and subscribe to Guelph Physics. They have fantastic events throughout the year. And you'll even see Orbax do some crazy things here and there.
Well, I don't know. All right, give her to Kareem. Fantastic. Well, thank you again for joining us. Not only do we run a YouTube channel, but we're also, of course, on all the social media platforms. You can, well, only on a select few, actually. You can find us over on Facebook at Guelph Physics or on Instagram at Guelph Physics to keep up to date. Thank you so much, everybody, for joining us. As I mentioned, we're going to try to keep these consistently going throughout the rest of the semester, at the very least. And next month's program, I believe, is going to be examining forensic physics with the Peel Police Department. So we'll take a look and see what that is. Thank you so much for joining us, everybody. As always, I'm the humble science communicator, the Great Orbax, and I hope you have a science-tastic day.